Well, hello everyone. Let's start with the problem for the night. So the problem this time is calculate the inverses of the following matrices if they're possible. This is 2.8 again from the book that we've been solving so far, Mathematics for Machine Learning. Right, so we've been given two matrices, but before we actually get to solving and finding out if their inverses are possible, a useful thing to understand is how are we going to proceed and why are we going to proceed that way. So I have some notes written here. Refer to those. So there's a condition. So just to check if so it's better to check if an inverse is possible and then find the inverse, like if it's possible. Otherwise, you'll be lost trying to find it when it doesn't exist. So it's always better to see if an inverse even exists. So you remember how when we had a matrix being multiplied with a vector x giving vector b, and we had to solve this equation for the vector x, and we had developed this intuition that the determinant of a must be not equal to 0. And the reason was this, so that we had trivial solutions. In this case, we couldn't actually solve it because either we would have infinitely many solutions or no solutions at all. We sort of have the same thing for this. So this is a matrix, its inverse matrix, and the identity matrix. And imagine these are three-dimensional square matrices. So I'll just write 3 down there. So it's sort of the same argument here that just the det of a is not equal to 0. Now you can make this more sophisticated, and I'm sure some people would like to talk about adjugate or adjoint matrices, but this is sort of the faster way to look at why this works. So this is just a very geometrical argument. If you're more interested, you can look up adjugate or adjoint matrices to make this more concrete. So given any matrix, you have to find its determinant, and if that turns out to be equal to 0, you cannot find its inverse, and if it's not equal to 0, you can find its inverse. Now since you're finding determinants and you're finding inverses, remember we'll only do this for square matrices. You can't invert a non-square matrix for obvious reasons because the dimensions won't match. So if 4 by 2, you can't really get its identity matrix, as that would have unordered rows. So argument and our working will only work for non-invertible or invertible square matrices. That's it. That's all we're doing today. So let's start with part A. Part A gives us the matrix A, and this has the values 2, 3, 4, 3, 4, 5, and 4, 5, 6. So as I said before, we don't want to be too keen on trying to find the inverse straight away. We need to at least first check if the inverse even exists. So to do that, we find its determinant, and A's determinant can be opened like so. So it would be 2 times 4.6 minus 5.5 minus 3.6 minus 5.4. I could have extended it, but I'm using another line for this. Plus 4, 3.5 minus 4.4. So I've opened the determinant based on the first row here. You can open it on anything else. If you find something's better, you can do that. And 4 times 6 is 24. This is 25. Minus 3, this is 18. This is minus 20. And plus 4, this is 15. Minus 16. This is minus 1. My bad. Minus 3. Minus 2. Plus 4. Minus 1. Minus 2. Plus 6. Minus 4. This is 0. Now this is most interesting. Since the determinant itself is 0, we cannot find an inverse. So had you not actually thought about if an inverse is or isn't possible, you would have been lost and you would have never found an inverse because an inverse isn't even possible. So there's value in sort of trying to step back and see if an inverse is even possible. We don't want to rush too quickly. So yeah, that's part A. Now let's see part B. So far we were thinking about seeing if an inverse exists or not. So in part B, they have given us a much larger matrix. My bad, I'll get rid of this. No point in having that there. And this time A is a 4 by 4 matrix. 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0. Right, so let's try to find the determinant for this. So I'll make a semicolon instead of an equal to. It's not exactly a continuation. So let's expand upon the first row because it has two zeros. Actually, something that would be better would be to expand along the this column. This is because it has three zeros, so you would actually have to only figure out one determinant. Or no, let's, for the sake of simplicity, still only expand it along the first row. So the first row would be 1, and then you would have the determinant of everything in here. So that would be 1, 1, 0, 1, 0, 1, 1, 1, 0. Now you obviously know the signs. This is plus minus, so on and so forth. So this is minus and this is plus again. So I'll pick plus here, 1. A determinant, that'd be 0, 1, 1, 1, 1, 1. And this would be 0, 1, 0. So this is what it would look like. We can figure these out. You'll have to expand this. Again, it's best to expand it along the rightmost column, but for the sake of simplicity, I'll still again go with the first row and I'll do the same here. If I do this, this is 1, 0, 0, 1, 1, minus 1. Sorry, this is 0. And this would be 1, 1, 1, 0, plus 0, so you don't need to think about this. Plus 0, so you don't need to think about that. Then minus, and then 1, 1, 1, 0. And then you have, now I'll just write x so that there's nothing there. And then there's plus 0 again, so again you don't have to think about anything here. So this is 0 times 0, so that's 1 times minus 1, minus 1 times 0 minus 1, minus 0 times minus 1, and that is minus 1, minus 2, plus 1, which is still minus 1, which is not equal to 0, and therefore this is invertible. So you found that part B, the matrix, is invertible. Now since we found that it's invertible, we can actually start our search for its inverse. Let's think about how you actually find the inverse once you know it's invertible. What you're effectively trying to do is solve this equation, right? So you're trying to, this, right? So we're starting with a four-dimensional one in this case. So let's make this example more concrete. So this is a four-dimensional A and a four-dimensional identity matrix. We know what a four-dimensional identity matrix looks like. It's 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? And what we really want here is to be able to solve for this. If you recall our examples from previous questions 2.1 through 2.7, some of them we've tried to solve systems that look like this. And we've tried to use Gauss-Jordan elimination there as well. Tried to reduce it into row echelon form and do everything. And what we noticed is that when we solve this, which is a modified matrix of sorts with this bar in the middle, and if you use row operations and eventually get this to look like I, then that effectively changes this to whatever you want there. So in this case, if we start with A and I, and we can somehow make this look like we can make this look like X, capital X, or some other matrix, and this can look like, my bad, one second, where's the eraser? Make this more clean. So if we start with, something like matrix A, and then we know this, right? It's four dimension, and we can eventually get I here, then this must have been A inverse. That's sort of the argument we're using. Because there is no way you can get I unless you multiply A with A inverse. There's no other way. And so this must have been A inverse. That's sort of what we're saying. This is fairly straightforward. Since we've already done this, I won't spend more time here. What I'll do is erase all of this. Yes, I know it's a new feature. One second. Yep. So let's start doing that. So I can write this down. And if I write this down, I've already written down the steps so I didn't waste your time too much. So we can start with something like 1, 0, 1 1 0 1 1 1 1 1 0 1 0 0 1 0, and this is the identity matrix. Obviously nothing fancy here. Right, so we will use row operations. We'll try to make this resemble identity matrix. We need to make this resemble identity matrix. So the first row operation I thought of was, now again the thing with row operations is you can have totally different orders, you can have totally different things. As long as we get to the same endpoint, we are fine. So my approach might look inefficient. I'm so sorry about that, but it is what it is, and it gets us where we want to get, so it's fine. So we switch R3 and R4, then it should just be 1 0 1 0. We'll just copy the first ones the way they are and replace this 1 0 1. I won't really rationalize this. The best approach with things like this is to start sort of from the top. So you want to make this correct and then this one, then this one, this one. I'm not really following that. It doesn't really matter. As long as you sort of can foresee how your operations will materialize, you are fine. And this does take trial and error. You might not be able to do it the first time. You might have to do it a few other times. So there is that. This will be 1 0 1 1 0 1 0 1 1 1. You can even try your own row operations as you go along with this, and that I would actually appreciate that. And I'm very sure that our answers in the end should match, because I did verify my answer using an online inverse calculator and it was actually correct. So I'm sure if you use any other row operation sequence, you will also get there. So this is R1 R3 and this is 1 0 0 0 1 1 0. One zero one. This is minus 1 0 1 0 1 0 0. Right, this will take a while. I'm so sorry. Like there are quite a few row operations, but it's okay. This is tedious, but there are far more efficient ways of finding inverses. It's just that they are not covered in this book. The the adjoint matrix approach, that's almost definitive. It always gets you an answer. This is more of a trial and error approach, so it may fail you. I think I already did this step. R2 minus okay, I did the opposite. Yeah. So 1 0 0 0 minus 1 1 0 0 1 0 1 0 minus 1 1 0 1. Is that minus? No, that's not minus. Sorry, that's plus. And then it's 0 minus 1 0 1 minus 1 1 0 0. And then this R2 goes to R2 plus R1. 1000 0 100 1 0 1 0 1 1 0 1. I feel like there must be a more efficient solution. Like I'm just using too many row operations and I'm not really. This is, to be fair, the first one I used, so I'm being lazy here. Like I could have maybe put in more effort and found a faster one. But yeah, it is what it is. I need to upload too many of these, so I guess yeah, we're almost there. Just two more operations. So R3 goes to R3 minus R1, and that will make this look like. I shouldn't have made a mistake anywhere because I got the answer correct the first time around. And if you do notice anything, I apologize for that. Shouldn't be anything though, pretty sure. Might just be bad handwriting anywhere. 0 1, so that's 1 1 0 minus 1 0 0 1 0. And then there's 2, so there's R4 goes to R4 minus R2 minus R1. Yep, and what this will do is get the identity matrix on the left hand side and get this matrix on the right hand side. And so you finally have it. A inverse 0 minus 1 0 1 minus 1 0 0 1 1 1 0 minus 1 1 1 1 minus 2. And this is, yep, that is A inverse. Thank you for watching. I hope you have a good morning, noon, afternoon, whatever, evening, night. Bye bye.